let's go into, you could run this, and it takes a little bit of work to set up the whole thing in SPSS. I can just verbally share with you what you would have to do. You'd have to set up one column as the dependent variable, putting all those numbers in. You'd have to have two other columns, one with one independent variable, the alcohol in the two levels, one with the other independent variable, the benzodiazepines in the two levels. And you could set all that up, and I can help you do that, and you could run the analysis. But let's look at the output screen, because most of the time it's looking at the output that you kind of have to, what does all this mean? And it's pretty exciting. Thanks for the yawn. No, you're okay.
I got up early this morning to vote. So
I know that feeling. Okay, so let's just look at this screen for a minute. So there are three important statistical effects to look at. What are they? What are the three important statistical effects to look at?
the two main effects in the interaction.
There you go. Is there a main effect of alcohol? Is there a main effect of pills? And is there an interaction between alcohol and pills? So the sums of squares. The sums of squares for alcohol. Do we want that number to be large or small? The sums of squares for alcohol. This number, the 4,800. We want it to be large. That number reflects the difference between the 90 and the 50.
Right.
The mean is 70. You do 90 minus 70 squared times 6. You get 2,400. Not that you need to know this. Same thing on the other side. We want that number to be large. If that number is large, that means the 90 versus the 50 is, and it is large. Do we want the sums of squares for pills to be large? Yes. How come that number is the same?
Because we had the same means for that.
90, the marginal means were 90 and 50 again. What about the interaction? 1,200. That number is going to reflect the non-parallelness of the lines. That's going to reflect how parallel or non-parallel the lines are. Were the lines parallel here?
No.
They were very non-parallel. So we get 1,200 here. What about the bottom line? It says error. I forgot to tell you something before, so let me share it with you now. When we did the one-factor ANOVA, I'm sorry, I feel like I'm missing some visual cues here, but that's okay. Here I can. Now we have everybody. So when we did the one-factor ANOVA, what was the numerator and denominator? That picture. The numerator for the F was what? Variance. Between group over variance within. Now in a two-factor, the variance between groups actually gets partitioned, broken down into, you notice here it says sums of squares between group at, what, 10,800? 4,800, 4,800, and 1,200. Guess what that adds up to be? 10,800. So it's actually partitioned into those three effects. So we have 4,800, 4,800, and 1,200. The error. What do we want the error to be? Large or small?
Generally, you want error to be small.
You want the error to be small. Now that's 108. The question is, could we actually figure out where that actually comes from? Did I make your life easy enough here or no? Let's go back to the visual here. 100, 100, 100. What is the variance within that group? 0. 78, 80, and 82. 78 minus 80 squared plus 80 minus 80 squared, 82 minus 80 squared. That sums of squares is 8. And then you keep going within each group, so you get a total of, I think I changed some of the numbers here. The sums of squares within group, you want that number to be low. It's 108 here. Degrees of freedom.
Is the same thing as error?
Getting close. Let me go down the line here. Don't worry about degrees of freedom between groups. That's not important. How many levels of alcohol do you have here? 2, unfortunately. Oh, I'm sorry. 2 levels of alcohol. Guess how many degrees of freedom we have for alcohol? 1. How many levels of pills do we have? 2, so 1 degree of freedom, and then alcohol by pills is just those 2 multiplied. It's 1 again. How does it come up with degrees of freedom for error at 8? Yeah, how many people do you have in the first group? 3. So how many degrees of freedom in that group? 2. You have 2 in that group?
So there's 2 in each group, so that's 8.
So that's 8. So that gives you the 8 there. Mean square is another term for variance. So the variance for alcohol is what? 4,800 over 1, which is 4,800. 4,800 for pills, 1,200 for alcohol, and then 108 divided by 8 is 13.5. So how does it come up with those 3 F values for alcohol, pills, and alcohol and pills? What does it do to get those values? Don't worry, we're almost there. How do you go from the variance for alcohol, pills, and alcohol by pills to the F score?
Of SPSS.
The magic of SPSS. But think about what it was.
Between groups over the variance within groups.
Bingo! For each one of these 3 effects, we divide it by the variance within group, the error. So if you took 4,800 on your calculator and divided it by 13.5, guess what you would get? 355. Is 355 going to be significant? Yeah, any day of the week. It says 0 there. 355 for the second one. 1,200 over 13.5, 89. Is that going to be significant? Yeah. So all 3 of these effects are going to be statistically significant. For the final thing maybe here, let's write out some F statements just so you know. Oh. This isn't going to work too well for me. I'm just going to go under. So for the F, for the A main effect, maybe we'd say F of alcohol. What are the degrees of freedom for the numerator? How many levels of alcohol did we have?
2.
We had 2 levels, so how many degrees of freedom? 1, comma. How about for the denominator, the within group? Degrees of freedom was the within group.
Still 1.
Not quite.
2.
It was the 8. It was the error line. What did that equal for the F score?
88.
Say again?
No.
What was the F score for the alcohol main effect?
355.
Yeah, 355 is good enough. And then you'd write what? P
It's less than
Less.
0.01.
less than 0.001 you can actually do. Real world statement there. This is very important, the real world statement. When people drink alcohol, what happens?
Their motor performance decreases significantly.
Yes, you wouldn't say anything about Xanax there. When people drink alcohol, motor performance decreases significantly by 40 points. End of story. So that's the main effect. There is a significant main effect of alcohol. Would it be the same thing for pills?
I don't understand why we're putting 8 in there, because I thought the 8 had to do with all the alcohol and pills population.
You do that. It's a good question. You do that because for this F score, this 355, the numerator is 1, the denominator is this 8. It's the error. It's the within group degrees of freedom, because you're dividing 4,800 by 13.5. So it has to be the 8. That's a good question. Does that make sense to you? You gonna be okay?
I'm okay.
All right. F of 1 and 8 again. Whoops, no star. Equals 355. Same thing, right?
Yeah.
What's the real world statement about the pills, though? That when you take
You take pills.
1 milligram of Xanax,
Yeah.
something I've never done in my whole entire life,
Significantly decrease in motor performance.
significant decrease in motor performance. Finally, the F for the A for the, we'd say alcohol times, actually it's usually called A by B, but we'll do alcohol times pills. Degrees of freedom, what? 1 comma 8 equals what? What was that value?
88 or 89.
89 is fine, and then what? P
That's the
.001 still. The question is, what's your real world statement there? That's the final part of this.
Performance significantly less when you take both alcohol and pills.
Exactly the way. There is a statistically significant interaction. When people take alcohol and Xanax together, it really diminishes motor performance. Are the effects additive? Are they additive?
No, they're.
It's actually considered multiplicative. That's where the times comes from. It's not a simple, that's where the 60 is. If the mean for the alcohol and pills together was 60, just take the alcohol, just take the pills, add them up together, there's no interaction. But we know that pharmaceutically, there is a there is an interaction, and here, for the statistical example, there is also an interaction here. So does this kind of explain the two-factor ANOVA situation? Comments or questions about this? Do you see two-factor ANOVA sometimes? The last thing I think we want to go over, boy, it's already getting dark out. It kind of is what happens these times of the year. Okay, we'll stop this recording now, and then the last thing we'll cover are the articles.